Okay, ladies and gentlemen, we're going to take a look at the comparison test. Now, the comparison test is a way to determine whether a graph is going to converge or diverge. Now, let's take a look from 0 to infinity of 1 over x e to the x dx. That is this orange graph right here in the middle. Now, the problem is I can deal with the infinite limit by saying, hey, limit as r approaches infinity, 0 to r, of this thing. But as soon as I attempt to go in and integrate this piece right here, I have a big problem. I can't integrate this, not using integration by parts, not by substitution, not by trigonometric substitution, not by anything that I'm aware of. And so, although I can deal with the infinite limit, I cannot deal with a non-integrable function. So what I need to do is use the comparison test. The comparison test says if I have something larger than f of x, so in essence higher than f of x, and if this converges, then if something bigger converges, then the smaller f of x must also converge. Now, I can use it in reverse, by the way, and I can say, well, I'm testing whether it diverges. So if I have this red graph that is smaller than f of x, so h of x is smaller than f of x, and if this red smaller graph diverges, then the larger f of x must also diverge. So what I'm doing is I'm hemming in f of x between two functions to determine if this one converges, f of x converges, but if something lower diverges, f of x diverges. Now, in our case, what we're looking for is I think what's probably going to converge looking at the shape of the graph. So what I need to do is I need to pick another function that is similar to this, but bigger. Well, if you take something and divide by something smaller, the number stays bigger. So for example, 1/2 is bigger than 1/3. So if I take 1 over e to the x, that's dividing by something smaller than if I divide by e to the x plus something else. So if I replace this function with 1 over e to the x, I integrate using my limits, and I do the integration, plug it in. I come up with 0 plus -1, or 0 minus -1, which is +1. That is clearly a finite integral, and that clearly converges. So if the bigger graph converges, then f of x must also converge. Okay, now, by the way, that doesn't actually tell me the value of this integral. It simply tells me that a value exists for that integral, because if this converged, then this here will converge. Now, I can also say that whatever this converges to, whatever its integral is, has to be smaller than 1, yet it has to be larger than 0 because it's above the x-axis, but it is smaller or lower than the graph that I integrated correctly. Now, if I take this and have a little different function, that's this weird wiggle. I also can't integrate this as it sits because of the square, and I don't have an x out front. So what I'm going to do is I need to replace it with something else. Well, what if I replace it with 1 over e to the x? Because 1 over e to the x is going to be larger than 1 over e to the x squared, because there's only one e to the x in the bottom rather than e to the x squared. So it's going to be dividing by less, which means overall it is bigger. Now, unfortunately, it's not always bigger. In fact, they switch places back here. So what I can actually do is break this graph up into 2 bits. This first bit, I am perfectly happy finding the integral of the original graph using my calculator, plug it in, let's say 0 to 1. Now 1 is chosen because that's where these two graphs intersect. And I get 0.7468. Well, that's good, that's a value. Now I need to find the integral of this. Well, I can deal within the proper limit, but I still don't know how to integrate this. So what I'm going to do is I'm going to switch and choose something larger. And if this larger thing converges, then the whole thing's going to converge. Well, we already determined that from 0 to infinity, it converges over here in our last example. So we know that this converges, meaning that if the red graph converges, then the orange graph will converge. We again don't know what it converges to. We just know that it does indeed converge. Now, I can go to my calculator and I can plug in some values. And I can plug in the integral of e to the negative x squared. The problem is I can't go from 0 to infinity using fn. I can't graph it and put the integral in that to infinity. What I can do is I can go from 0 to 1 quite easily. That's where I come up with the 0.7468. But over here, I can't do that at all. Although, to at least get an estimate, I could integrate this to say some large number. Well, it doesn't actually take a very large number. I went from from 1 to 100, and I got 0.886. I'm sorry, I went from 0 to 100, but I came up with 0.8862269. Then I thought, well, maybe I can get to an estimate by using a smaller value. I went from 0 just to 10, and it also was 0.88662269. And so by simply integrating, since this is at 1, you can see it gets very small very fast. By integrating, this whole thing should be approximately 0.88622269. The problem is, I don't know what it is exactly without a CAS system. So I can use the comparison test to determine whether something converges or diverges, but I can't tell you what it converges or diverges to. That requires use of a calculator. But you do have the official test, and it does work for both positive and negative infinity. This is one of the examples we looked at. You can use Simpson's rule to find an approximate value. Or if you have something in the neighborhood of something like this equation, we end up with the integral from 1 to infinity of 2 plus sine x over square root of x dx. If we think that this graph is going to diverge, we would want to find something smaller. So to find something smaller than this value, well, something smaller than this would be if I had something less than here. Well, sine x has to be somewhere between -1 to +1. So the biggest this number on top could be is 3, and the smallest it could be is 1. So if I just replace this with 1 over square root of x dx, that means whatever's on top here is smaller than what's up here, meaning this graph is going to be lower. So instead of having this, I can guarantee that my 1 over root x, is going to be smaller. If this diverges, this has to diverge. If this converges, doesn't tell me anything. I'd have to find something up above to see if it converged as well. In fact, what you find is that our new 1 over x diverges, so therefore the orange graph is going to diverge. So in this case, we're going to get this to diverge, and since it's lower, this also diverges. That is the comparison test. Again, it does not give you actual values. It only tells you whether something converges or diverges.